Hello guys, so welcome to the eighth video of the CSES problem set DP series, and today we are going to discuss this problem, counting towers. So if you haven't read this problem, please pause the video and try for 15 to 20 minutes and come back if you can't think of any approach, right? So this question is of medium difficulty, and I had to watch an editorial or watch an tutorial to do this. So let's discuss the approach and let's first discuss the problem. So your task is to build a tower. So basically, you have been given a height and you have to build a tower, right? You have an unlimited supply of blocks whose width and height are integers. So what you have been given is a tower, is basically a height. So what they want is a 2 cross h height tower, right? And they don't care how what type of bricks you use to construct that tower. They can be bricks of 1 cross 5, 1 cross 6. As long as they are getting a tower of height h, they don't consider anything, right? There is just one this thing, like our width cannot be greater than 2, right? Our width can be only 1, 2. These are the only two possibilities for our width of any block, right? Of any block consisting this, we can have only width 1 or 2, right? And we can have our height maximum, right? That's a simple, obvious, observation. We can see that we can have a width of either 1 or 2 in any of the blocks, right? So given h or n, you can say n, how many different towers can be built, right? So we have to find the number of towers we can build by placing different type of blocks. All right. And mirrored and rotated towers are counted separately if they look different. So what does this statement means? This statement means that if we consider these two heights, then we can see that these two blocks are same. These two towers are same because they look same, right? But if we consider this block, right? The mirror image of this block, the mirror image of this block would be this, right? Sorry, right? And these two towers, of course, look different. So these two are considered separately, right? And similarly for rotated towers, if you rotate this tower on rotation, it would look like this. And these two towers are different, right? There can be symmetric towers, and we would not consider symmetric towers. All right. So we have been given number of tests, and each line contains an integer n, the height of the tower. So how do we approach our problem? We know that in DP we have just this one trick. We have to break our problem to different sub problems, right? So how do we break our problem to different sub problems, right? So let us identify firstly the problem. So the problem is to generate a tower up to height, right? This is the problem. So we know that if we know a tower of h minus 1 height, right? This is what we do in DP, right? We assume that we have filled up to h minus 1 and there is just one block to be filled, right? So what are the cases we have here, right? So, but this question is a little bit trickier than the others. We would see how. So because there are many cases over here. So if we are at the ith block, we can see that the state of the ith block depends on the previous block, just the previous block. The ith block depends on I minus 1th block. How? If I minus 1th block is of width 2, right, is a tower of width 2. We do not consider the height of the I minus 1th block because that doesn't really matter. Because what matters is that if it is of width 2 or width 1 or two blocks of width 1, because that what matters. We don't want to, we don't, we are not interested in the previous states of I minus 1 because that's of no use to I, right? So how can we construct I? So these are the possible ways. Firstly, we can create a new tower from here, a new block. We won't extend the previous block, we would just create a new block of width 2, right? This is the first case. And we would extend it or not, we would consider that in I plus 1, right? That we won't consider here. That if we want to consider, we want to expand our I to I plus 1, that would be considered on I plus 1, right? That's a point to note here. So if we are at our ith block, what we can do is we can start making a block from of width 2, right? This is the first possibility, right? We don't expand here. Oh shit. Yeah. Okay. So that's our first possibilities. That's our first possibility that we can make a new block of height width 2. What is the second possibility where we find where we make a new block? It is where we make two blocks of width 1, right? These are the possibilities when we make new blocks. Sorry for the bad handwriting. Can't help it actually because I'm typing with the drawing with the mouse actually. And the other two possibilities are when we expand from I minus 1. So I minus 1 has only two possibilities, that it was a block of this, it was a 2 cross something block, or it was a it was two blocks of 1 cross 1, right? And we can expand. How can we expand this two block? This is fairly easy. We just expand it. There is no any nothing related then, right? Because we just expand the previous block, and we know that there is a fixed width, so we can't help it. We just create a new block. We just expand it. But in the case of two tiles of one block, two tiles of one width, what we'll be doing is that we have to make some cases here. First case would be there that I extend both of them, right? I extend both of them. And second case would be that I extend one of them and I completely block the other, right? I create a new tile of width 1 here. The third case is exactly the same as the second case. It's just that I just rotated their mirror images, right? So these are the three possibilities I can have with these with one blocks. All right, and there is no cases in width two block because if we want to extend, we would extend, right? There is no certain rule there. And if we want to create a new, these are only two possible options, right? So we saw that how we are breaking our problem. So what we are doing is that we are considering. Okay, let us consider this. We are considering. We know that we know the number of ways till ith one, ith position, and we want till I minus one. Sorry, and we want to find the number of ways in the ith position, right? This is what we do in DP, right? And there are some cases here which we should consider now, right? So let's jump to for the previous problem. Let's jump to the recursive and the tabular form what we will be dealing with, right? We would make an n cross 2 matrix. So what does this matrix represent? So dpi 0 would represent the number of ways to make two tiles of one width, right? There are, if we don't consider all these cases, if we just delete all these, so what is the basic criteria of differentiating? It is just one this. Either I can have a 2 cross 1, either I can have a width 2 block, or I can have two blocks of width 1, right? These are the only two cases I can have, right? And DPI1, okay, I won't be actually just copy paste it. Make one tile of two widths, right? So represent, right? So what we DPI1 would represent the number of ways to make one tile of two width and one tile of two tiles of one width. So we understand how we are how I hope you understand that how we are defining our DP, right? So let's see the relation, the recurrence relation we can have. I don't know, it is not actually a recurrence relation, but yeah, the DP relation. Okay. So DPI0, remember DPI0 would represent the number of ways to make two tiles of it, right? There are two cases. First case, we expand, right? Second case, we make a new one, right? Similarly, on I1, we have two cases, right? If we make a new one, we know we don't it doesn't really matter what was on the I minus one position. It was a one cross, it was two tiles of one or two tile or one tile of one. It doesn't really matter because we are making a new one, we are making a new making a new foundation, right? So it doesn't really matter that what was the state of I minus one position. So we just add both the states of I minus one position. But if we expand and we are and here please note that we are expanding and we are expanding two tiles of one width, right? There are three cases, right? First case, actually they these this is the critical part where you need to think why it is why it is 3 into dp minus. All right, so this is the actually answer that if we expand to 1 cross 1 to 1 cross 1 tiles, then our number of ways would be 3 into dp I minus 1 0. Now why 3 into dp I minus 1 0? So we saw that there are three cases and it is actually because of it only. So in every case we notice that there has to be two tiles of one width, right? In every case, even if we are making a new one and expanding one, and if we are making exactly sorry. Oh, okay. Sorry. Actually, not 3 into 2 into, because there are two cases, right? Not three. There are two cases. If we are expanding, right, we can expand one and leave another as it is. We can expand both. Okay. Oh, sorry. There are actually three cases because we can expand a mirror image as well. Sorry, my bad. Sorry. Well, so it is actually, I hope I didn't actually confuse you. Yeah. So there are three cases when we expand both, when we expand one, and when we expand either of these, there are further two cases that if we expand the left one or the right one, right? And why all these states represent dpi minus 1 0? Why? Because the dpi minus 1 should contain two tiles of width 1. This is the this is the number of ways of making two tiles of width 1, right? DPI 0. So DPI minus 1 0 represent the number of ways to make two tiles of width 1. Here, here also, and here also. So if three of them are same, then we would just be adding these three up, which means 3 into DPI minus 1 0. So that's a little tricky part to be explained and as well as to be understand. So please understand what I'm saying, right? Because it is a crucial part here. Why is this code working? Why is this 3 into dp I minus 1 working? Right? It is because we are just interested in the I minus one, and we because we just want these two tiles, these two tiles of one width in the I minus one step. We don't want two widths, right? That's why we are doing this. Similarly, here what make a new one. It doesn't really depend on anything, right? Would be the same. But if we are expanding, we need to have a two cross one, a tile of two widths, right? So I hope it is clear. So if we expand a tile of width two, then we just have this one option that the I minus one tile should also have a tile two width, right? So there, I don't think I missed anything, right? Because let us just recap the theory of the question. It doesn't really matter what is the state of I minus one position if we are considering ith position, right? Oh, sorry. If we are considering ith position, it really matters what is the state of I minus one position. For that, it doesn't really matter because we are not interested in that. We are interested in just ith one. And there are these two cases. We can expand or we can make a new one. Making a new one has two cases that DPI and both of these cases are exactly same because uh, we don't really consider what is in the IS one I minus one as position if we make a new one. But if we expand, we are concerned about that and hence different formulas. If we want to expand a two cross one width, a width of two tile, then we have to have a two width tile on the I minus one step. But if we wish to have expanded the one cross one tiles, then we can have three different cases due to which we have 3 into dp I minus 1 0. So I hope it is clear. Now let's just jump to code. But on a very serious note, please just pause the video or maybe just close this window and try to code it yourself because I have really given you much hints that you need it, right? So let's jump to code part now. So there is a little bit twist, right? This is the explanation. It's just actually nothing but it's just twisted, right? I1 is the number of ways when we have one tile of it two, but in the consider okay, it is exactly the same. Okay, sorry. So it is exactly the same. But what we are doing here is that we are pre-calculating all the values because when I didn't pre-calculated it, I got a TLE, right? As you can see. What was the first step that I did? I created a DP of n cross 2 size, and I just did this is all the recurrence relation part, right? And I what would be the output? Yeah, I forgot about this. What would be the output of my answer? What would be the answer? So the answer would be of course n minus 1 0 plus n minus 1 1, right? Because we want to make a tower of height n, right? So we want to make a tower of height n. We want all the ways, so we just add these two because these are just like this was the first approach that I had. That I did the DP computation inside the our T loop, the test cases loop, and I got a DLE at test case 4. But when I did when I did pre-computation beforehand for n is equal to 10 power 6, I didn't get a TLE. So that's a tricky part to note here. So overall time complexity is order of n only. But if we consider, if our test cases are large enough, then our time complexity is order of 1 because because we are just pre-computing it once. The pre-computing cost is order of n, but the query cost is order of 1. So we really did a great job here, saving the time complexity. So it was a pretty tough question, I guess, and it falls in the medium or too tough bracket. I'm not sure if it is hard or easy because I'm not really an expert DP yet. So I don't really think that it is easy, but I don't really think it is that hard. So I would give it a medium thing. Right? So it is a medium question. Now let's have a spoiler about edit distance. The edit distance between two strings is the maximum number of operations required to transform one string into the other. So the allowed options are add one character to string, remove one character, and replace one character. Okay, this is pretty easy question. Very easy question. I mean, if you have done okay, if I just said that word, then you might just get it that what would happen, right? And it is pretty obvious that we have to have LCS here. This is the question of longest common subsequence. So it's a pretty easy question. We can solve it really easy. It is. And yeah, that's it for now. And bye bye.